Hello students, in this video we'll see an example of orthogonal diagonalization. Let's consider the symmetric matrix A, which is 6, -2, -2, 3. That's clearly a symmetric matrix. Let's orthogonally diagonalize this. Orthogonally diagonalize. Okay. We know that if we have two distinct eigenvectors, eigenvalues for a symmetric matrix, so if V and W, just remark that if V and W eigenvectors for distinct eigenvalues of A, and if A is symmetric, then V is perpendicular to W. Okay, let's prove that, of course. So if I look at the inner product of V and W, right, what I can do is I want to consider this, and what I'm going to do is I'm going to say that this V corresponds, I'll say this corresponds to lambda 1, this corresponds to lambda 2, okay? So what I have over here is I'll take this over here, and I'm going to I'll put a lambda 2 over here, right? Then what that is that's going to be, that's the same thing as V comma A applied to W, but A is equal to A transpose, right? So this is going to be A transpose, this is going to be V and then A transpose W because it's symmetric. I'll put the transpose on V now by properties of transpose. This is going to be A, V, W, right? My vectors everywhere here, make sure it makes sense. And AV is equal to lambda 1, right? So this is going to be lambda 1, V, W. Right, now these are real over here, so I'm going to pull out that lambda 2. So we've just shown over here, this implies that lambda 1 VW is equal to lambda 2 VW. Okay, but I know that lambda 1 and lambda 2 are not equal to each other, right? So I can subtract those things. That forces VW to be equal to 0, right? So that's exactly what we get over here. So they are orthogonal to each other. Great. And so that means since they're orthogonal, I know that the eigenvector matrix is going to be an orthogonal matrix, so I want to normalize in the right way so we get the right transposes. So let's solve the eigenvalue problem for this matrix over here. I'm going to look at determinant of A minus lambda identity equals 0. Is the same thing as saying that the determinant of 6 minus lambda, -2, -2, 3 minus lambda is equal to 0, right? And so I'm going to have a lambda squared, then a negative, let's say -6, -5, and -9 lambda, and 18 plus 18, then a -4 is equal to 0. So my eigenvalue equation is lambda squared minus 9 lambda, and that's going to be a plus 14 is equal to 0, which we can easily factor as lambda minus 7, lambda minus 2 is equal to 0. So my eigenvalues are 7 and 2, so lambda is 7 or lambda is 2. Great. And so now let's find the eigenspace that corresponds to, let's say 7 first, okay? So let's look at the eigenspace E7. That's going to be what equation? I'm going to subtract off 7, so I'm going to have a 6 minus 7 is going to be a -1, -2, and I'm going to augment this with 0, 0. And down here we have a -2, and I plug in 7 over here, I'm going to have a -4, okay? So this clearly row reduces to a 1 and then a 2. And so I can choose a eigenvector over here. My eigenvector V1, V2 is just going to be what? It's just going to be a, what does that mean? I'm going to put the bottom one to be negative over here. So I'm going to let this be just a 2 over root 5 and then a -1 over root 5. Of course, I've chosen the root 5 to make that sure that this is a unit vector over here. So this is my V hat, and that's going to be a unit vector. Okay, excellent. Let's find the eigenspace corresponding to 2. E2 is going to correspond to what? Now I'm going to subtract off 2 from the main diagonal. I'm going to get a 4, then a 2, and negative, of course. And I augment with zeros. Down here I get a -2, and then when I plug in 2 over here I get a 1, right? So this clearly row reduces to what? This row reduces to 2, and then -1, 0, 0. We can see the orthogonal structure popping up already, right? And so I'm going to choose W1, W2 to be what? Let's see, I'm going to choose it to be 1 over root 5, then 2 over root 5. Okay. We can see that these vectors, that's also a unit vector. Now we can clearly see that v and w are perpendicular to each other, right? So now I'm going to form my matrix over here, my matrix P, which is going to be 2 over root 5, and then negative 1 over root 5, 1 over root 5, 2 over root 5. And we can clearly see from this that the determinant of P is equal to 1, right? Determinant P is equal to 1. And the rows are orthogonal, so that says that P inverse is P transpose. P inverse is P transpose. And so P inverse is just going to be what? It's just going to be 2 over root 5, and then 1 over root 5, and then a negative 1 over root 5, and then a 2 over root 5. Okay? And of course we can see this corresponds to what? This P transpose has the positively oriented rotation, this is the negatively oriented rotation, okay? So now we're done, because now what we say is the following. We say that A, my matrix A, which is 6, negative 2, negative 2, 3, is equal to this matrix P over here, which is 2 over root 5, 1 over root 5, negative 1 over root 5, 2 over root 5, and then 7, 2. It's my diagonal. And then what? And then over here I'm going to have a 2 over root 5, then a negative 1 over root 5, then a 1 over root 5, 1 over root 5, then a 2 over root 5. Excellent. And as typical, you might say, well, why don't we do this? This factorization is actually much nicer because this is P transpose, it's an orthogonal matrix. These are just rotation matrices, right? So I have a structure of rotation, diagonal stretching, then anti-rotation. Now, even more important than that is if we look at this abstractly, it's more important to realize the following is true. So what I have over here is I really have something of the form over here that looks like what? That looks like this is V hat, W hat, and then my diagonal matrix 7, 0, 0, 2, and then V hat transpose, then W hat, like that, transpose. And so if I multiply this out, we see that A is really equal to 7 V hat transpose plus 2 W hat transpose. And this is true in more generality too. So what I've done over here is I've written A as the sum, as the weighted sum of two projection operators. This is the projection onto V. So this is really 7 projection onto V hat plus 2 projection onto W hat. And so this is a very, very simple version of the spectral theorem, which holds in general for real symmetric matrices that can decompose a symmetric matrix into a real symmetric matrix into the sum, or if it's an n by n, of n different weighted projection matrices. It makes the decomposition very, very straightforward. Thank you very much.